Good morning, and thank you for coming. I'm going to be talking about composing quantum algorithms. And this just means when you compose algorithms, it just means that you have an algorithm that calls another algorithm as a subroutine. So you imagine you have some main or outer algorithm. And here I'm drawing this is like just a classical deterministic straight line program. So each of these circles represents some basic operation. They're different colors just to emphasize that they're potentially different operations. But then there's also some dotted circles here, and these represent potentially more complicated operations that you require in the algorithm or in the program, but you have not said how they will be implemented. But of course, you need to specify that. So in order to complete this algorithm, you need a subroutine that implements this sort of dashed circle. You can use the subroutine to kind of fill in these dashed like holes in the algorithm. And it's sort of understood here that if you would take this subroutine and fill it in everywhere that there's kind of a hole in the algorithm, you would get a complete algorithm that's fully specified in terms of basic operations. There's a number of reasons why you might want to do this. Sometimes you already have a very nice algorithm for a subtask that you think would be useful in whatever problem you're currently trying to solve. This can also just be a nice way of organizing your algorithm if there's like some process that you do many times. Maybe you want to abstract it into some kind of subroutine. It also makes it easier to reuse parts of your algorithm later. And it can also make the algorithm easier to analyze. And the subject of my talk today is going to be the complexity of composed quantum algorithms. When we compose two efficient algorithms, sort of the minimum that we hope for is that the result is an efficient quantum algorithm, or efficient algorithm in general. And actually, this is one of the main motivations for why polynomial time is our sort of measure of efficiency, rather than just something like linear time. Because if you compose polynomial time algorithms, the result is also a polynomial time algorithm. But we can say something, of course, much more fine-grained than that. In particular, if your main algorithm has L basic operations and Q subroutine calls, so Q here stands for query to subroutine, not quantum. We're not doing anything quantum yet. And your subroutine has T basic operations, then obviously the complexity of the full program, it's very easy to see, it will be Q times T plus L. Okay, so this is for the simple case of deterministic algorithms, but we're going to be working towards talking about quantum algorithms, and then the more natural analog and the more fair comparison is with classical randomized algorithms. These are classical algorithms that are allowed to make random choices. There's two different kinds of randomized algorithms that we can consider: Monte Carlo algorithms and Las Vegas algorithms. In a Monte Carlo algorithm, we say it solves the target problem if on every input, the output is correct with probability at least 2/3. Whereas in a Las Vegas algorithm, we require that on each input, the output is correct with probability 1, which is obviously a much stricter requirement. However, the condition for the time complexity is more relaxed for Las Vegas algorithms. So for Monte Carlo algorithms, there's some running time t, after which the algorithm always must halt. And so there must be this sort of finite running time. This t is what we call the running time, and it's the measure of complexity of a Monte Carlo algorithm. In contrast, a Las Vegas algorithm, its measure of complexity is the expected running time. So generally the running time would be a random variable, and its expected value must be finite. It could run much longer than this. It could even be that it potentially runs for an unbounded number of steps, but the measure of complexity is just the expected number of steps that the algorithm takes. So for example, consider this Las Vegas algorithm for the problem of black box search, which, if you recall, is the input is an n-bit string x, and you want to find some I such that x sub I, the ith bit, is 1. And we'll assume that there is such an I. So here's an algorithm that solves this problem. It just repeatedly chooses a random I and checks if xi equals 1 and outputs, if so, it outputs I, and then it's done. Okay, it's not difficult to show that the expected running time of this is at most n, but there's no bound such that this always halts after that bound. So for any b, the probability that this algorithm is running for more than b steps is always non-zero. It's exponentially decreasing. That's why the expected number of steps is finite, but it could run arbitrarily long. In contrast, here's a Monte Carlo algorithm for search, and it's very similar, except that we only repeat at most 3n times. And if we haven't found some I such that xi equals 1 after 3n steps, then we just output something arbitrary like I equals 1. Now, if we do that, we're probably wrong, but we can show that this happens with probability at most 1/3. And so this is a Monte Carlo algorithm for search. And of course, since we only run for 3n steps, the complexity of this is big O of n. So on the one hand, Las Vegas algorithms have a stricter requirement on their success probability, but they have sort of a more lax requirement on the running time. So you might think that these two kinds of algorithms are incomparable. But it turns out that Las Vegas algorithms are strictly stronger than Monte Carlo algorithms. Because if you have a Las Vegas algorithm, you can always turn it into a Monte Carlo algorithm by just truncating it, which means you just stop after something like 3 times the expected number of steps. And so this, and then you just output something arbitrary. So this is still correct by Markov's inequality. This is still correct with probability at least 2/3. But then this will always have running time at most big O of whatever the expected running time of the Las Vegas algorithm that you started with was. So we can always turn a Las Vegas algorithm into a Monte Carlo algorithm, but going the other way is generally not possible. And actually, this is an example of just the truncation I talked about. This algorithm on the left is obtained from the algorithm on the right by truncating. An important conceptual point is a Las Vegas algorithm actually a real algorithm? Because you don't actually ever have a computer that can run forever. So of course, you can always just truncate the algorithm, and then you get a Monte Carlo algorithm. I would say that's definitely a real algorithm, the Monte Carlo algorithm. But if you say, I'm going to run this Las Vegas algorithm, you actually will always truncate it, because there's always some maximum amount of time you would be willing to run it for. So in some sense, we could say that Las Vegas algorithms are sort of a conceptual model, and Monte Carlo algorithms represent sort of real algorithms. Both kinds of algorithms can be composed in a rather straightforward way. So let's start with Las Vegas algorithms. Suppose you have a Las Vegas algorithm that uses Q subroutine calls and L basic operations. So what this means is this is an algorithm that if you were to instantiate the Q subroutine calls with some like oracle that returns whatever the expected result is perfectly, then you would get a Las Vegas algorithm. So an algorithm that is always outputting the correct answer. If you plug in to these subroutine calls a Las Vegas subroutine, then it's always going to return the correct answer. And so the result will still always have the correct answer. And so the resulting algorithm will be a Las Vegas algorithm. And generally, like these Q, L, and T will be random variables. And so the running time will be a function of them as shown here, Q, T plus L. And the expected value of this is given by this expression. And here we've used linearity of expectation and also the assumption that the number of subroutine calls is independent of the amount of steps the subroutine takes, which is a very reasonable assumption. Okay, and we can use this to show something rather simple and concrete, which is we can show an upper bound on the zero error randomized query complexity of composed functions. So let me say what these things mean. The zero error randomized query complexity of a function f is the minimum number of input queries, so times you sort of read a bit of the input, needed by any Las Vegas algorithm for f. And a composed function, if g and h are functions on n and m bits respectively, their composition is a function on m times n bits. So we think of its input as being n kind of m-bit strings. And then the output is just what you would get if you apply h to each of these m-bit strings. Then you get n bits. And then you apply g to that. So that's the composed function. So now let's just see why this claimed result is true. Suppose you have a Las Vegas algorithm for g that makes q queries to the input. In query complexity, we only care about queries to the input. We don't care about other operations. And you have a Las Vegas algorithm for H with Q prime queries to its input. You could turn this into a Las Vegas algorithm for the composed function with Q times Q prime queries to the input. And that's because you're going to replace every, and this is going to compute the composed function because you're going to replace every query where G asks for like what's the ith bit of my input by a call to H. Let's suppose that these are optimal, so these have sort of optimal expected query complexities. Then we can see that of course the zero error randomized query complexity of the composed function is at most the expectation of this algorithm, which we could upper bound like this because of course Q and Q prime would be independent. And then this gives the claimed result. Okay, composing Monte Carlo algorithms is very similar, but there are some small differences. So again, these Q, L, and T can be random variables, but we do, like the running time should be some number after which we always terminate. So for example, we can assume that the subroutine runs in time, like at most some constant times the expected value, because if for some reason it runs longer, we know that we could always truncate it after some constant multiple of the expected value of T. And but the bigger difference is that these subroutines have error. So this is only guaranteed correct with probability 2/3. And this outer algorithm, it's also guaranteed correct with probability 2/3, but that's assuming we replace the subroutine calls with like something perfect, something that does not have error. So generally, if one of the subroutine calls returns the wrong answer, we have no guarantee that the algorithm will be correct. So if we try to just compose these, we'll end up with an algorithm that is only correct if all subroutine calls, all Q subroutine calls, return the correct answer. And that happens with probability like 2/3 to the Q, which is extremely small if Q is like not 1 or 2. So there is a way around this, though. There's a solution, which is to use majority voting. Majority is a procedure where it calls some oracle that returns some values, and it just outputs whatever the most common value that it sees is. And so if we wanted to plug a subroutine in to an algorithm like this, we'll instead compose the algorithm with majority doing a bunch of calls to the subroutine, and it will just see what most of the subroutine calls output, and it will return that. And the right number of calls to guarantee that with high probability all Q subroutine calls are correct is log Q, where this Q in this font is like something like the expected value of Q. And so this means that we do, if we use this kind of procedure, then we do get an algorithm that is a Monte Carlo algorithm. It's guaranteed correct with probability something like 2/3, but it now has a log factor in the complexity. So its running time is going to be like the expected value, like this. Okay, recall that when we compose Las Vegas algorithms, we don't get log factors. Oh yeah, I should mention also we get this, we get this analog of the result we saw before, but for bounded error randomized query complexity. So this R of some function f is just the minimum number of queries needed by a Monte Carlo algorithm for f. And so we get this upper bound on the bounded error randomized query complexity of composed functions, but it now has a log factor. Okay, as I was saying, if when we compose Las Vegas algorithms, remember we don't get a log factor, right? And I said before that in some sense, Las Vegas algorithms aren't real algorithms. And so maybe you think, well, okay, I now composed my Las Vegas algorithms, and now I'm going to truncate to get a bounded error Monte Carlo algorithm. I'm actually going to run that. If you're going to do that anyway, you might think, okay, well, I could also just first truncate all of my algorithms and then compose them as Monte Carlo algorithms to get a Monte Carlo algorithm out. But you, of course, should not do that, right? Because if you do that, then you get a log factor. So you should, if you have Las Vegas algorithms, you should keep them as Las Vegas algorithms until the very end, and only do the truncation once. Every time you do this truncation, it introduces error. This is kind of an important conceptual fact for later in the talk. So even if Las Vegas algorithms are not really real algorithms, they are definitely a useful model for composition. Okay, I'm already sort of allowing you here in pictures to use multiple subroutines, and the results that I just stated,
they generalize to the case of multiple subroutines. So, for I ranging over some set, maybe you have make qi calls to some subroutine that computes some different functionality, and you have a subroutine for that functionality that takes ti basic operations, and then we can get Las Vegas algorithms or Monte Carlo algorithms with these complexities that are, again, almost the same except for a log factor. Okay, so now let's get to the main subject of my talk, which is composing quantum algorithms. So the first indication we had that things are not so simple in the quantum world of composition is a result from 2002 by Berman and DeWolf, showing that there are two functions whose zero-error quantum query complexities are both constant, and yet the zero-error quantum query complexity of their composed function is linear, which is much bigger than the product of the zero-error quantum query complexities of the two functions. So the most basic thing we would hope for, that composition preserves efficiency, is not even true for zero-error quantum algorithms, which is in contrast with what we saw for zero-error randomized algorithms. However, the issue here, this is maybe like not such a great start, but the real problem is not like, it's not that composition just fails completely. The problem is that insisting on getting out a zero-error quantum algorithm, that seems to just be too much to ask for. If we're happy to get a bounded error quantum algorithm for the composed function, then things do compose very nicely. This works roughly the same as in the randomized world. This is just, this randomized statement is just a weaker statement of this, so of course it holds. So if you have zero-error quantum algorithms and you want to compose them, you can get a bounded error quantum algorithm, and that's no problem. So I think, if anything, the reason that this fails for zero-error algorithms is really because zero-error algorithms is like not really the right model for quantum computation. So this is fine. Now here we kind of recover the classical picture, but there's there's another twist to this story, because if we start with bounded error quantum algorithms and we want to compose them, we get sort of the same thing without log factors, which is in contrast to the case of randomized algorithms where there's a log factor, and we actually, that log factor is necessary. So this is nice. This is actually, in some sense, we can do better in this setting than what we can do in randomized algorithms. So yeah, so this is all sort of not very fine-grained and just in terms of query complexity, but this is all to show that when you are composing quantum algorithms, things just work quite differently from when you compose classical algorithms. The situation is just different. So this is what's coming in the rest of my talk. I'm going to talk about how if we're satisfied to get a bounded error algorithm out, composing algorithms, actually it's not obvious how to do it, but it does work like how randomized algorithms work, as long as you're happy to get a bounded error algorithm out. So okay, that's nice. We get sort of the same thing as we get for randomized algorithms. And we can, even better, we can compose bounded error quantum algorithms without incurring log factors, so that's better than classical. So I'm going to talk about, this is basically like a more fine-grained time complexity version of this query complexity result down here. And then I'm going to mention an application to QMA amplification. It's the same technique that we use to remove log factors can be applied to QMA amplification, and I think this is sort of evidence that these techniques are somewhat fundamental and have applications in other areas. So to start off, let me talk about composing quantum algorithms, why it's not obvious that it works like randomized, but it does actually work. So usually a quantum algorithm is thought of as a circuit, which looks something like this. This is kind of like the deterministic algorithms we saw, except there are, of course, multiple lines. They represent usually different qubits. And we have rectangles instead of circles. Each of these rectangles is a unitary. They might just be like elementary gates that only act on like one or two of the wires. But they're also allowed to be subroutines. And then, just like in the case of deterministic algorithms, it's necessary to specify a circuit that implements the subroutine. And then, if you plug the circuit into this algorithm, you get a new algorithm. So that seems actually to work easily enough. But the problem is that quantum algorithms are not deterministic, and deterministic algorithms are not even a good analog of quantum algorithms. Just as a randomized algorithm can call different subroutines at random, a quantum algorithm can call subroutines in superposition. And that's actually exactly what Grover's algorithm does. So let's see an example of that. We're going to consider the problem of AND of ORs. So that's the problem where the string, the input is some string that we kind of view as being broken up into blocks of potentially different sizes, k1 up to kn. And for this function, we want to know, is there any block that's all zeros, basically? So to compute this function, you compute the OR of each block. That gives you n bits, and then you take the AND of these n bits. And you can solve this problem, for example, by doing quantum search for some I from 1 to n, such that the OR of the ith block is 0. And if you find 1, you output 0, and otherwise you output 1. If you're familiar with Grover's algorithm, you might remember it looks something like this, where each of these v's is the same basic unitary, and they're alternated with queries to the bits that we're searching over. So in this case, each query is going to controlled on some wire containing I. It's going to compute the OR of the ith block. And so we can instantiate this query using a subroutine that's also just going to do quantum search for some j from 1 to ki, such that the jth bit of the ith block of input is 1. And for that, we can use Grover's algorithm again, which runs in about square root of ki steps. So maybe now you see a little bit what the problem is when you compose quantum algorithms. So we want to call a subroutine on a superposition of different I, but different I have circuits of actually different lengths. So how can we call circuits of different lengths in superposition? Actually, in the circuit model, we sort of can't do that. The best you could do is you could have a circuit of one length that, when it's finished, it's kind of just waiting for the other circuits to terminate. So you're kind of intuitively going to wait until all branches of superposition are done before you can apply V2. And so you get an algorithm with a complexity that's like the square root of n times what's the cost of a query? It's the maximum overall I of the square root of ki. And we know this is far from optimal because earlier works have shown that you can solve this problem in something that looks much more like an average than a maximum. And but these don't use any sort of composition of search. You can get this better result by just a dedicated algorithm for this problem. Okay, so it sort of looks like if you compose circuits, you can't get a very good complexity compared to what you would get with a randomized algorithm, right? A randomized algorithm would never wait for the maximum number of steps. And in general, what this looks like is the following. If you have any outer algorithm and that calls a subroutine controlled on some wire that contains some I that could be between 1 and n, and then for each value of I, you have a circuit that implements that subroutine. If you naively combine these using circuit composition, then the best you could sort of get is this complexity, where L is the number of steps of the outer algorithm, Q is the number of subroutine calls made by the outer algorithm, and Ti is the running time of the ith subroutine. However, it turns out that we can actually do better than this. So we can show using something better than just naive circuit composition that we can get a complexity that looks like this, where now instead of a max, we have a kind of weighted average. And what are the weights in this average? Let me explain. This is something called the average query weight. So if psi t is the state before the tth query, so for example, the state just before we do the first query would be called psi1. And then we'll define qit to be the probability if we measured that state that we would measure that we were about to query the ith subroutine. And then qi bar will just be the average over all queries of this. So we get something here that is like, so this is, this qi bar is a bit like the quantum analog of the average at any query, like the average probability that you query the ith subroutine at any subroutine query. Okay, so I've just sort of tried to tell you that we clearly only get this naive complexity, and that's the only obvious complexity. But now I'm going to try to tell you why actually we could expect to get this better complexity indeed, but it will not work if we just do naive circuit composition. Let's look for inspiration to classical composition, where it's kind of more obvious that we get some kind of an average complexity. We often imagine a randomized algorithm as a tree with different possible paths that you could take. So we kind of like enter the tree at some sort of entrance, and these boxes represent some sort of a coin flipped where we make a random choice among different paths, and then these circles represent some computation possibly implemented by a subroutine. And we keep going until we get to one of these leaves, which I call them terminals. And every terminal is either accepting or rejecting. We can, of course, use other structures to visualize classical, like randomized algorithms, like a directed acyclic graph or a random walk on a graph. But if we don't care about space without loss of generality, we can always imagine a randomized algorithm looking like this. Okay, so let's see how we can sort of visualize one run through this algorithm. We're going to imagine that we start with 1 unit of liquid flowing into this graph through the entrance, and it spreads out over the graph. And already after a small number of steps, some of the liquid is on some of the terminals, which the probability that the amount of liquid on the terminals after 1 step is like the probability you stop after 1 step. And if we kind of keep going like this, and then the amount of liquid on a terminal is the probability that you end the algorithm on that terminal. Now, importantly, the location in the tree does not encode your whole state. It just encodes like what coin flips you've seen so far. So we imagine that this liquid is also carrying around some extra information. Now, this picture is, of course, very different from a quantum circuit diagram, right, which looks something like this. The quantum circuit also has a bunch of lines in it, but they mean something very different from the different lines here. Right? The different lines in the quantum circuit are like the different qubits or the different subsystems of the algorithm, of the space that the algorithm is on. So they're sort of like different systems that are a tensor product decomposition of the full state space. On the other hand, the different lines in the randomized algorithm, they represent also subspaces of the kind of like space of probabilities on which the random variable encoding your like position in the algorithm is distributed. But these spaces combine to make the full space, not in a tensor product, but actually in a direct sum. So if you sort of take the direct sum of all of these different probability spaces, you get the full space. Okay, so on the one hand, we have quantum algorithms in a circuit diagram. They're very nice for if we want to view the tensor product structure of the space, which, by the way, we're not really taking advantage of here because we just have every gate covering all the wires. But it would be nice if we wanted to show that certain gates are local. But on the other hand, in this randomized algorithm, we can see sort of this direct sum decomposition. But this is not like a quantum versus classical thing, because of course, in a quantum algorithm, we can also compose the space that the algorithm works on. We can also decompose it into a direct sum of spaces. We very often do that when we analyze the algorithm. We can't see those different spaces here, though. To see them, we have to kind of like look at the algorithm from a different angle. So this is me turning the algorithm to a different angle. Okay, okay. So what do we see here? We don't see anything yet, but if we look at this algorithm from sort of this different conceptual view, we can view it much more like in the randomized algorithm. So here, again, we can imagine that we have sort of 1 unit of liquid coming in, and that 1 unit of liquid is like, it's basically showing that we have amplitude 1 on the initial state, which is, for Grover's algorithm, is the all zero string. And in Grover's algorithm, the first thing we do is we do Hadamard gates to get a superposition over all possible I. And we can visualize that. Here, the liquid will represent like the squared amplitude on a different subspace. And so we visualize that sort of similar to a uniform distribution in the randomized case. So the liquid equally distributes across these different wires, and each of them represents a particular I. So this is kind of like some decomposition of the space of the algorithm into n subspaces that are in direct sum. Okay, what we do next in Grover's algorithm is we apply a query, and the query does not change the amount of amplitude on any of these spaces. It does compute the function value. We can't see that here. That's some of the extra information carried in this liquid, but the amount of amplitude doesn't change. But importantly here, this query operator, this OR that's controlled on this I wire, it decomposes into a direct sum with respect to these same subspaces. It's a direct sum over different I of some sort of different operations. And so we can actually kind of break this box up into separate boxes. I'm drawing them now with circles, like in the classical algorithm, though of course they might also be implemented by a quantum algorithm. Okay, so if we sort of squint a little bit, this starts to look kind of like how we visualize a classical algorithm, except of course it can't be a tree. As long as we don't measure, the different paths can and should come back together. And Grover's algorithm is going to just be this sort of same thing repeated over and over again. So it might look something like this, where each of these dashed circles is some sort of function that needs to be implemented somehow. And the implementations of these functions need not be the same length. And so we might end up with a picture that looks something like this. Okay, so now let's visualize what a run of the algorithm would look like. So applying Hadamard's puts us in a uniform superposition. And then after one step, some of the liquid is already ready to have the next unitary applied, but most of the liquid is not. So is it bad if we just send the liquid through this box, which represents a unitary, before the rest of the liquid has caught up? It actually turns out to be completely fine. So if we just send this liquid through as it's ready, then at some later point in the algorithm, some of the liquid catches up. That's fine. By linearity, it all just adds up to the right thing. And if we run this procedure for something like the expected total path length of the algorithm, then most of the liquid will be through. Only some unlucky liquid that always took really long paths won't be through yet, but we'll still get a bounded error algorithm. After some constant times the average path length. Okay, so of course, that's not what happens if you compose algorithms using naive circuit composition. As I kind of argued, you get something like this. And that's because in naive circuit composition, what you do is, once you're finished very early on some of these subroutines, but you're like, well, I can't apply the unitary until my whole state is done. So you just wait. You kind of just keep doing the identity until everyone is done, until you've waited the maximum number of steps, and then you apply the unitary to the whole state. So imagine in a randomized algorithm, if your subroutine call finished, but you were like, well, I actually still have more allotted time for the subroutine call, so I'm just going to wait. That's a bit like what you do in naive circuit composition. In order to get an algorithm to behave more like the quantum analog of a randomized algorithm, we need some kind of a model that is more like the quantum analog of a randomized algorithm. And the first candidate is quantum walks, which are the quantum analog of random walks. There's a generic way of transforming any quantum algorithm into some kind of quantum walk, some kind of rather general quantum walk, that preserves the complexity. And then, for reasons that you maybe believe from the pictures I showed, quantum walks compose very nicely. And then, you can always turn the quantum walk back into a specified circuit at the end, and it will have this sort of better complexity where we get an average instead of a maximum. Okay, so naive circuit composition does not give you good complexity, but using a better sort of technique, we can actually get composed algorithms that have this complexity. And this actually looks very much like what we get in the randomized case. To see that, notice if we move this Q inside the sum, then the product of Q and this bar IQ, that's the expected value of a random variable I'll call QI. And what that random variable is it's like if you would take, for every query in the subroutine, for every query in the main algorithm, you would take the state of the algorithm just before that query. You would take all of those states. And then you would measure them all. And QI is the number of times you would measure that you were about to query I. So it is the expected value of Qi is like the quantum analog of, in a randomized algorithm, the expected number of calls to the I of subroutine. And this expression is actually exactly what we get when we compose Las Vegas algorithms. Okay, so I should mention that when you do this quantum walk composition, even if you start with algorithms that have 0 error, the results will actually have a small bounded error. And that's fine, that's a very natural model for quantum computers. But what we haven't talked about is what if the subroutines have error? And so that's what I'm going to talk about next. Okay, we just saw how if you have a quantum algorithm that computes, let's be concrete and say it computes some particular function f, and it does so using queries to subroutines that compute different functions g sub I. We can, and we have subroutines for g sub I, we can kind of compose those to get a fully specified algorithm for f that has this many operations. And we saw how to do that using composition with quantum walks. But we can actually get the same result using, actually we can even get a more general result, using a model that is generalizing quantum walks and is sort of a maybe conceptually nicer for composition, called transducers. So transducers in some sense have quantum walks as a special case, or at least for any quantum walk there is a transducer. So I'm actually going to draw transducers the same as quantum walks. You can kind of imagine a bit that they're the same thing. And transducers are a model of quantum computing such that you can map any quantum algorithm to a transducer, even if its behavior is an arbitrary unitary, even if it doesn't compute a classical function. And then you can map a transducer back to a bounded error quantum algorithm. And transducers have a notion of complexity that gets sort of preserved in this mapping. And like quantum walks, transducers compose very nicely. So one reason you might use transducers is to compose functions or to compose quantum algorithms like this. So for simplicity, we have been assuming that our subroutines have no error, but what if they do have error? If our subroutines have some small bounded error, what happens is that when we turn them into transducers, they also have some small bounded error. And all of those errors add up, similar to when you compose algorithms, so that the resulting transducer is like overwhelmed by error, and then so is the resulting algorithm. It just computes total garbage. Okay, but we saw one solution for this in the case of classical algorithms. What we could always do is we could always, before we turn our algorithms into transducers, we could first use majority voting. So compose them with majority voting, which calls them a bunch of times. So there's a log Q overhead. And then now the error of the resulting algorithms is small. And so when these small errors add up, it's still not too big. So this works, but it gets you a log factor in the complexity. And I mentioned before that we can actually do without this, we can actually get rid of this log factor. And the way we do that is instead of using majority voting, we use some kind of a quantum analog of majority voting called purification. Purification is a bit like majority voting for transducers. So we'll map our subroutines to transducers that have error like 1/3 each, but then we'll use purification to make that error smaller, so that in the end the errors still don't add up to anything too big. But the really remarkable thing is that the overhead that we get from purification is constant. And so we don't get a log factor in the complexity. And because this overhead is constant, we could actually make this error arbitrarily small. We can make the error as small as we want in the transducers, so it's essentially 0, and then adds up to 0. But then when we turn it back into an algorithm, we will still get bounded error. Always at the step where we go from transducers to algorithm, bounded error is introduced. So in particular, this does not allow you to take a bounded error quantum algorithm and then get rid of the error and then in the transducer and then turn it back to a quantum algorithm that has no error. No, the algorithm that you get at the end, when you sort of truncate the transducer into a quantum algorithm, you will always get, there will always be some constant error added. Okay, I'm gonna now say a bit about what transducers are and how this purification, this quantum analog of majority voting for transducers, how this works. I don't want to formally define transducers, so I'm going to kind of explain them at a high level. We can visualize a transducer as a graph. with an entrance and an exit. And it's not a coincidence that this looks exactly like how we're visualizing quantum algorithms. Like in our algorithms, we imagine that the edges are pipes that can hold liquid, but the transducer also has like an action. And that action, on every time you sort of iterate the transducer, each node will pull water through from the left and put it out the right. So for example, if we start with 1 unit of liquid on the entrance, and we run one iteration of the transducer, it'll pull the water through, and then one more iteration, it'll pull it through. And with every iteration, the water is being pulled through the graph. And if you keep going until like some constant multiple of the expected path length, then most of the water has made it to the exit of the graph. Okay, now imagine that you could somehow pre-fill all of these pipes in the internal part of the graph with water. It's not clear what that means because, of course, this will add up to more than one, so it's not like any state. But just bear with me. Like imagine you had more than a unit of water. You had all the water that you wanted, and you could fill this graph. Now, if you run the transducer once, every vertex is going to pull the water through from left to right. So you maintain the state of the internal graph, but now in one iteration of the transducer, you've moved water from entrance to exit. Moving water from entrance to exit, that sort of metaphorically represents something we would want to do. So that's kind of good. But of course, it doesn't make sense for you to say, well, why do you have this pre-filled configuration of water? What does it even mean if your probability adds up to 1? But anyway, just sort of conceptually, this is kind of turns out to be interesting. So we call this the state of the pre-filled water. We call this a catalyst because we can kind of like, in one step, do the operation we want to do, getting water from the entrance to the exit, and if we have the catalyst, and then we also keep the catalyst. Okay, but what does this sort of mean operationally? Well, it turns out that there is an algorithm, a quantum algorithm, that moves the state from the entrance to the exit with bounded error using a number of iterations of the transducer that's like the size of the catalyst. So it's like the total amount of water needed in the catalyst, or since ultimately the catalyst is going to be a vector, it's the squared norm of that vector. Okay, what does it mean, move state from entrance to exit? As I've already kind of alluded to, the entrance and exit represent some starting state and some goal state. So that's something that we would want to do. And iterations of the transducer, well, in one iteration, you kind of move water from left to right, but like in an actual algorithm, I mean, a transducer is actually just a unitary in sort of mathematically. Okay, so we call the sort of catalyst size the complexity of the transducer. It's the squared norm of the catalyst. So in this example, the size of the catalyst, or the squared norm of the catalyst, would be 1/4 times the sum over all path lengths, which is just the average path length. So that's kind of natural to be the complexity of this transducer. But more, the complexity of the transducer, if we kind of turn a transducer into an algorithm, its complexity will be related to this. And so that's why we call this the complexity. Okay, now what if we have an arbitrary quantum algorithm? I said that we can map it to a transducer. There's actually some different ways of doing this, but here's one way. We can always map a quantum algorithm to a transducer that is like a line graph with t nodes. And the entrance represents sort of the initial state at time equals 0. So a unit of liquid on the entrance means that we have a unit vector on the initial state, or a unit of amplitude on the initial state at time equals 0. And then the exit represents kind of the final state of the algorithm, the state we would get by running the algorithm at time equals big T. And so we want to get a unit of water to the end of this because that will mean that we have the final state of the algorithm. We have sort of completed the algorithm. Again, if we kind of pre-filled all of these edges with water, then in one iteration of the transducer, the water would be kind of pulled through, and we would maintain the sort of pre-filled water, and now we would have moved water from the entrance to the exit in just one iteration. But what does it mean mathematically to have a unit of water on each of the edges in this line graph? Well, just like I said, a unit of water on the entrance represents having the state c at time equals 0. A unit of water on the first edge represents having the state like u1 applied to c, so the state after one step of the algorithm in time equals 1. And then the next edge is like the next state of the algorithm in time equals 2, etc. So if we take the sum of all of these states, this is the catalyst. So this is like, you might recognize this as, this is like an unnormalized history state. And mathematically, if we take the initial state and this catalyst, and we were to apply the transducer, which mathematically means that we apply this program unitary, which looks at the time register, applies the appropriate gate, ut+1, and then increments the time register, thus pulling everything along, pulling everything one step of the algorithm. Then the result is that we get the catalyst back, but now instead of the initial state, we have the final state. And okay, so this catalyst is like this kind of history state. And remember, the norm of this catalyst is kind of going to tell us what the complexity of this transducer is. And it's pretty easy to see the norm of this is t minus 1. So it kind of makes a lot of sense that you start with an algorithm that has complexity t, and you turn it into a transducer where the complexity is also approximately t. Okay, so the concept that like a history state, like an unnormalized history state, can be a sort of catalyst, and its norm represents the complexity of the transducer is kind of a key point here. So try to keep that in mind as we move now to looking a little bit at how we can do purification with transducers. Okay, imagine that you have some randomized process that you can run that outputs a random bit, and p is the probability that you get 1, and you want to decide if p is at most 1/3 or at least 2/3. Okay, so this process represents like having a randomized algorithm, and you want to kind of amplify its success probability. So you want to decide this about p with, like, let's say, probability much better than 2/3. What you could do is you could take an infinite line and do a biased random walk on this line. So you'll start at 0, and at every step, what you'll do is you will, wherever you are in this graph, you'll like flip your bias coin, which is like making one call to the randomized algorithm. And if you see 0, which you will with probability 1 minus p, you of course don't know what p is, you'll move to the left, and otherwise you'll move to the right. And basically you're just trying to say, like, am I biased to the left or am I biased to the right? And then after some number of steps, each step representing, like, it can be implemented by a call to this randomized process, you can just look at what side of 0 you're on to decide whether you were biased to the left, meaning like p is less than 1/3, or you're biased to the right. And this is actually exactly simulating majority voting. The quantum analog of this setup, you have some unitary oracle, and on input ket 0, it outputs a state that looks like this. And this is kind of like the setting where you have a quantum subroutine that you want to amplify its success probability. Although, just for simplicity, I'm assuming that your subroutine like can uncompute any extra space that it used. So it's just a single qubit output for simplicity. Okay, so what we can do is we can do a kind of a quantum walk, but it will be on a slightly different line. And actually, we'll sort of do the transducer of defined by this line. So for kind of a bit intuition/inspiration to get us started, imagine walking on this line like the following randomized process. You start at 0, and you keep walking, and if you ever return to 0, you guess that p is at most 1/3, and you stop. And otherwise, you guess that p is at least 2/3. Let's analyze this classical process. When p is at most 1/3, we can show that actually, because you're biased to the left, you're at least twice as likely to move left as right. We can show that with certainty, you will eventually hit 0. And the expected number of steps before which this happens is just constant, because you're really, you're moving to the left twice as often as you're moving to the right. And actually, for sort of similar reasons, if we look at the transducer of this process, there's a catalyst of this form, and this is kind of like, this is representing, this is like a history state of this randomized process, essentially. And the squared norm of this is just the expected number of steps, and so it's constant. And remember, like, the size of catalysts has to do with complexity, so this being constant, that's very good. So this seems like really great so far. But actually, everything we've said is completely classical, and there's also a very big problem with this algorithm that you may have seen, which we will see when we analyze the p at least 2/3 case. Well, first of all, okay, there's some probability of error. So even when p is greater than 2/3, you might return to 0, but the probability of that is bounded by 1/2. So, okay. The worst thing is that this takes infinite steps. Like when p is at least 2/3, you either return to 0 and then you output and you're wrong, or you run forever. So this is a stupid algorithm, but I mean, it's classical. It's just a classical algorithm. We haven't said anything quantum so far, so we shouldn't expect too much. Okay, what we can do in the quantum case, now we have to kind of take advantage of the fact that we're actually in a quantum setup. We're not just running this randomized algorithm. What we can observe is that if our quantum oracle outputs this state on input ket 0, then on input ket 1, it must output a state that looks like this, which is basically the same thing, like, possibly up to a global phase. That's just by the fact that this is unitary. This is basically the same state, except it has a minus, but also p and 1 minus p have their roles reversed. And for roughly this reason, we can also get a good catalyst in the p at least 2/3 case, and we can sort of show that the transducer, also in the p at least 2/3 case, has no error. So it actually perfectly distinguishes these things. And it has a catalyst that looks like this. And in the p at least 2/3 case, this state has bounded norm, because then 1 minus p over p is at most 1/2. So in this case, p over 1 minus p is at most 1/2. And in this case, 1 minus p over p is at most 1/2. And so the result is that we get a transducer with a complexity big O of 1, meaning that we have an algorithm, or not an algorithm, very importantly, not an algorithm. We have sort of like a transducer that makes a constant number of queries to this subroutine and can perfectly distinguish these two things. It is very important to really mention at this point that if we take this transducer that is somehow perfectly distinguishing these cases in a constant number of queries, if we turn that back into a quantum algorithm, it will have bounded error. It will not have 0 error, right? So we can't like take the error out of a quantum algorithm, but we can take the error out of a transducer. And that's a very useful thing to do if you're going to compose them. Okay. Now I want to just mention an application to QMA amplification, but since I'm sort of running out of time, I'm just going to kind of like give this one for the experts. QMA is a long-standing open problem whether QMA is equal to QMA1. It's known that you can amplify QMA verifiers to get both the soundness and completeness sort of exponentially small, or soundness and completeness error. We show how to make the completeness error doubly exponentially small using the same kind of technique as purification. And to do this, we incorporate a state that's pretty much like this into the witness, where p is the success probability. So when p is bigger than 1/2, this is going to be bounded. This is like basically our catalyst, but it's truncated at L. We can also show if we take L to be infinity, we get a perfect completeness of sort of a version of QMA where you have the verifier gets to have an infinite dimensional register that they can increment, but nothing else. If we take L to be 2 to the poly, then that's how we get this result here. Okay. And also recently, my co-author Freek Witteveen and Scott Aronson showed that this is also optimal for any black box construction. Okay, so in summary, 0 error composition to get a 0 error algorithm works very badly for quantum, but that's probably because 0 error is the wrong model. We saw that naively it looks like 0 error to bounded error also doesn't work very well, but actually we saw that it actually works fine, basically just like how randomized works. And we get something even better without log factors if we take bounded error quantum algorithms to bounded error quantum algorithms using transducers. And we had this nice application to QMA amplification. But I kind of want to just say, I think transducers are some kind of analog of quantum Las Vegas algorithms, but this is very different from the classical case. And if you want to know why, you can ask me, because I'm really out of time. But I think that our application to QMA amplification, for example, I think suggests that this is sort of a really fundamental idea. It's very unexplored what this means, and I think there are probably more applications. So I will stop there. Thank you very much.
Thank you, Stacey, for very nice talk. So we can take few quick questions. Hi, great talk. Thank you. So when you were making the catalyst for like a fixed initial state, like you were appending unitaries and then you superpose them. So if you like wish to like like do the run the algorithm for like a longer time, then you'll have to keep updating the catalyst again and again. Or like if you want to use a different starting state, then is there like a way to like because you'll have to remake the entire catalyst, which like if you're not using the same state for the same number of steps, it like becomes a bit uh difficult. So is there like a way to like generalize this to like a more general set of states, or like you don't have to like look up the catalyst?
So yeah, importantly, the catalyst, as maybe you observed, it does depend on the initial state. So you kind of would need different catalysts for initial states. But in the algorithm, you never actually construct the catalyst. Like making it, first of all, it's like not normalized, so you'd have to make some normalized version of it. But then, if the catalyst is a history state, making it would, I guess, require you to kind of run the whole algorithm. Um, so we don't actually assume that you make the catalyst at any point. It's actually just like kind of a tool in the analysis of the algorithm. If you can sort of show that the catalyst exists, then you can show that the algorithm will work.
Okay, okay. Thank you.
Any more questions? Yeah.
Thank you. Thank you for the talk. Just to see if I understand roughly, is it okay for me to think of like in the world of transducers, basically BPP and RP are the same thing? Is that the...
Um, yeah, I think that's like a good question. So now that allows me to say the thing I wanted to say but didn't have time. So does it sort of, yeah, transducers being quantum Las Vegas algorithms, I think it's like, I wouldn't say it's the same thing as sort of like, I guess it's ZPP. I wouldn't say, because I mean, ZQP actually is defined, and it's defined in terms of like these zero error quantum algorithms that are really like the same as zero randomized algorithms. This is like quite a different thing. Like one thing that's different is you can turn bounded error quantum algorithms into these kind of quantum Las Vegas algorithms. That's not true classically. But they're also, in some sense, well, in a real sense, they're weaker than classical Las Vegas algorithms, because one thing, when you truncate a randomized Las Vegas algorithm, you will, with probability 1/3, you won't get the right answer, but you'll know, right? You'll kind of like, if you find the answer before you get to the truncation point, you'll know it's the right answer. And that's not the case with the bounded error quantum algorithms you get from truncating transducers. They're just regular bounded error quantum algorithms. They're wrong with probability 1/3, and you have no idea if you're in that 1/3.
Yeah, please.
Thank you for the very interesting talk. I have a question that, as far you used as an example of the quantum algorithm, the unitary operations.
Yeah.
And will you consider the non-unit, I mean, the with unitary then post-selection, so alternating, or you consider that you can use some algorithm with finite probability, some of the probability less than 1, then you can apply oblivious amplitude amplification, something like that, to make it probability as far as possible to 1, and then we can apply your scheme. So how do you consider extending to that case?
Okay, so I think there's still room for extension to some non-unitary things. So in some of the results I mentioned, it's sort of explicitly known that if you have a like what's called a variable time quantum algorithm, so that's like a quantum algorithm where you kind of assume that at every step of the algorithm there's a measurement that you perform that tells you whether you're done, but that measurement also sort of commutes with all future operations. So you can, without loss of generality, not do that measurement until the end. So it's some kind of a model of quantum algorithms that could have varying running times, but you can still analyze them like unitary algorithms. That's why in some of my results for quantum, actually listed here, I have like the expected number of steps. This ETI is the expected number of steps that the ith quantum subroutine takes. Why should that be a random variable? Only in the model that I just described, this variable time model. So in that sense, we can handle sort of probabilistic quantum algorithm, like not entirely unitary quantum algorithms. But I think there's more room for developing in this direction.
Okay, thanks.
Yeah, last one.
Yeah, thank you very much for your talk. I just wanted a small explanation where you explained the transducer.
Mhm.
Uh, could you explain why you take a sum of the initial state and the catalyst instead of only applying the catalyst? I mean, why the sum?
Yeah, so this is, again, this is like really a conceptual thing. So it's not that like, because of course this state then of the initial state plus the catalyst has norm more than one. So it's not that, you know, at any point you're ever like actually applying this. It's more of like a conceptual thing that you could use to prove that that a transducer works. As stated, but okay, so but why we sort of like this, so this is just a mathematical statement. This isn't actually like that anything is happening in the real world, but it's an important mathematical statement for analyzing transducer algorithms. And the reason we take the catalyst and the initial state is because the point is that what we want to show is that if you apply, like this box is actually the transducer. A transducer is always just a unitary. If you apply the transducer to this vector, right, it's not a state, it will sort of preserve the catalyst, and instead of the initial state, now you'll have the final state. So in order to kind of analyze this transducer, so we prove that this mathematical statement is just used in the analysis, and the mathematical statement that we need to show is that this is a catalyst, and what it means for this to be a catalyst is that if we apply the transducer to the catalyst plus this state, it preserves the catalyst and gives us the final state.
Thank you. Just please explain what you call purification, error purification.
Like, okay, in pure, I mean, I of course left out like a lot of details of purification, but the thing that you can, like, the parallel with purification is in purification, the catalyst was also kind of like a history state, but it was like a history state of an infinite process, but where the kind of, like, it's supported on infinitely many time steps, but you know, its overall, like, its norm squared, which is like sort of the, I don't know, expected number of steps that this process takes, is bounded. So sort of we use something that's like a history state of kind of like a Las Vegas algorithm, right? Which the history state of a Las Vegas algorithm would also be kind of infinite dimensional, but with like exponentially decreasing amplitudes, so that it could have a bounded norm.